Buenas tardes a todos, mucho gusto, gracias por la puntualidad al conectarse. La conferencia del día de hoy la va a dar el doctor John Dankert, él es PhD en bioquímica, tiene más de 20 años de trabajar en la industria de pollo, ha trabajado con las grandes compañías en Estados Unidos y el día de hoy nos va a nos va a exponer el tema la eficacia antimicrobiana del ácido peracético en los procesos de desinfección de alimentos. So John, you can start right now. Time is yours.
Okay, well, thank you very much for inviting me. I was asked to present on some of the things that we're doing in the United States on the antimicrobial efficacy of peracetic acid use in food processing. I'm going to focus mainly on the poultry industry because that's what we, Evonik in North America, are mainly doing, although we do many beef plants as well. Just to start, Spectrum is the name of our 22% peracetic acid concentrate. It is a green chemistry in that it breaks down to natural products, not dangerous, acetic acid, vinegar, and hydrogen peroxide, and then eventually to oxygen. It has a broad spectrum of efficacy. It kills both gram-negative, gram-positive bacteria, kills many fungi and the like. We have the same chemical as a disinfectant for broad spectrum use in a lot of different industries, including the medical industry. The chemistry is not foaming. There's no rinse required. It does dissipate all in and of itself. It has no lasting technical effect. For the United States, that's the definition of a processing aid. It can't, when the customer buys it or you consume the product, there is no technical effect. There's no antimicrobial activity left in it. If it did have any antimicrobial activity left on the chicken or the meat, you would have to be on the label, and we have to label it as a preservative. And nobody wants a preservative on their chicken packages. It works over a very wide pH range. We pH 1 to, we have customers that can use it at pH 12.
John, sorry,
Yes,
excuse me
sir.
a moment. Dave, no sé si usted o Estuardo pueden ayudar con los subtítulos, que creo que está teniendo problemas los asistentes de ver la parte de subtitulación.
Ok, gracias. Ahorita vamos a estar trabajando en ello. Y les estarán mostrando ahorita. Creo que ahorita ya aparecen incluso.
Okay, sorry, John, it's about the subtitles, so people is saying that they didn't see it, so sorry, you can continue.
Okay, and if I'm going too fast or slow, let me know as well. The chemical for use in the plant has no dangerous fumes for the use solutions, and it's not corrosive to stainless steel and many other common plastics and that tubing used in the poultry industry. Now, what peracetic acid is, its chemistry, is a combination of acetic acid, vinegar, and hydrogen peroxide. And you're all familiar with hydrogen peroxide. It's got this double bond of oxygen, and it's a highly reactive bond. You know this because if you ever used to put it on cuts and things like that, you drop it on a cut and it fizzles, giving off the oxygen gas. It's highly reactive, too reactive for most uses in the industry. Once it hits a body of water with chicken in it contains a lot of organic compounds, and that dissipates the effect. So what peracetic acid is we take these two chemistries, acetic acid and hydrogen peroxide, combine them, and we put that I'll say energetic bond onto acetic acid. We release water in the process. So now that active bond that can do damage to things is now locked onto this peroxyacetic acid molecule. And what we're hoping is that somehow that can be utilized. And in this case, to break down, back it down into vinegar, acetic acid, and then somehow to do some destruction to what we're targeting. We're targeting these pathogenic organisms on poultry and meat. This is just sort of an overview of processing. We call this first processing. or evisceration in the States here. We have the arrival of the birds, following through stun and bleeding, taking the feathers off, rehang. That's where we put them on a shackle line so they can be eviscerated by machines. Oh, I didn't know. I'll go back. Then it goes through one or more bird washes, goes through a few sprays, water cabinets again, then through a chill system, maybe or maybe not a post-chill intervention, and then to further processing. And each of these brown arrows here represent possible application points for application of antimicrobials in this step, in these steps. And this is different for every chicken plant is different. They all do the same thing, but just on the way they handle the product, the way that what they do, what their management can handle, is where they determines where they add or don't add any intervention point. In this case, peracetic acid. Starting here again from post-chill, we have cold rehang, and that's the term I'm going to use. That's where the birds' carcasses are now cold. They're rehung onto a shackle line that takes them on into second processing or further processing. We have the separation of the dark and white meat usually, and then there's belts, shackles into combos or tubs for transport, and to make many, this is just one plant, just a few of these things I'm talking about. Trimmed breasts, these can be then further sliced into thin slices. They can be further sliced into strips for stir fries and the like. Wings and party wing segments, regular drumsticks, thighs, boneless, skinless thighs, and they're all packaged. And all along here, any of these steps, any of these belts, shackles, interventions can have a spray cabinet or a spray rinse on them. Again, depending on how the plant performs in most of their other applications. This is an example. This is a chicken plant that we are in. This is a post-pick intervention, a PAA intervention. So the birds have been defeathered. They still have their paws on, you can see, and they're ready to go into the evisceration side of the plant. They're still on the shackle line where they were stunned, bled out, defeathered, and the like. Oh no, excuse me. This is after they've been rehung. That they're going. In this case, they're fooling with the paws still on. In this case, these are ready to be eviscerated, but they're going to go through a rinse after they've been defeathered with peracetic acid early on. Their paws are going to be removed, and then they're going to go through the rest of the process. Your options here are a spray cabinet or an immersion dip tank, where you can actually take the birds on the shackles and as you lower them into a tub, a trough, filled with chemical before they move out to apply the peracetic acid. So this can be either a spray or an immersion dip tank. I'm going to spend a little more time here because these are the data, what I'm going to be showing a lot of in this talk and what I'm going to be talking about. What we have here is along this axis, we have the log bacteria. In this case, 0 to 5 logs. So this is 10 bacteria, 100, 1,000, 10,000, 100,000. And we have the level of bacteria on a carcass, and we have two different types of carcasses here, two different types of bacteria we're assessing. We're looking at aerobic plate counts, or regular aerobic bacteria, or Enterobacteriaceae. The Enterobacteriaceae species is kind of a model, many folks here believe, for Salmonella-like species. Anyway, before these birds, so they've been defeathered, they're just as you see them entering the cabinet, they get to spray rinse, and then we see a reduction. And this particular spray rinse is about 300 to 400 ppm peracetic acid. In a dip tank, 6 to 7 second dwell time, and an overflow into the dip tank of about 2 to 3 gallons per minute of fresh peracetic acid. And you see, because of that, we get a decrease in the levels of both the aerobic and the Enterobacteriaceae type of bacteria. So The APC and EBC are used as, for this case, as indicator organisms for pathogen production. You can't really go in here and look for salmonella incidents and the like because there's just too much salmonella. It would take too many data points. Here we have thousands, tens of thousands of counts on each sample, and you can get enumerated data that's enumerated and that you can actually get statistics for. And this is how we're, in case anybody's not clear about how what we're doing here for, and this is for all assays, how all assays are collected. First, we put either a whole carcass or a number of parts of poultry. In that case, it looks like wings, in a sterile rinse bag. We add buffer. 400 milliliters is the standard amount. We then take the bag and rinse it, shaking for about a minute. Then we collect the rinse for testing. And this is just standard. We have 400 mils of sterile buffer. You see it pouring into the bag. We've got the bag and the chicken. In this case, it's parts. We shake it and we collect the sample, and it results in a sample that's a nice size for shipping. Most labs need only this amount to test for Salmonella, Campylobacter, and the indicator organisms, as I talked about. So the question, oh, no, I went too fast. Why would anyone use resources to start a processing to reduce pathogens? Well, it turns out that I can't think of any plant that does not do this. These antimicrobials are applied in a stepwise manner along the processing. And this is what's known, everybody here calls it a multi-hurdle approach to limit pathogens. And the idea is to reduce the bacterial load in a stepwise manner. One intervention, aside from cooking, is the only thing I can know, has ever eliminated all pathogen. So one intervention is not going to do it. Each step in the process presents an opportunity to put a dent in the bacterial population on a carcass or part until the next reduction step. This makes it easier for the next step to reduce pathogens. So the idea, it's easier to clean a cleaner bird, and we're going to see that that's true. Here's a little bit different. We've got APCs all on this slide, EBCs all on this slide. In this case, for this plant, we're looking at the difference between two lines, two processing lines. So these are two evisceration lines, either looking at APCs or EBCs. And don't worry about the numbers here, but just look at the trends. So this is a way we can actually compare differences between the lines to see if we're getting this nice reduction through the process. And it actually just takes us past, into, and through the chilling process. So here we have APCs going down in a general direction and EBCs. This is the, in general here, one thing that we do see a lot is we see a bump after evisceration. And this is common because we have birds that are intact pre-evisceration. We eviscerate them, pull out the organ pack and that tends to get, you can break guts, things like that during the evisceration process. You can get an increase here, but then subsequent steps lead to a reduction and incremental reductions in the pathogen load, making it easier. The history of the plants here is that if they wait till the end, there's lots of trouble in reducing the pathogens. Again, this is all done. I haven't mentioned Salmonella here or any of the data here because they're all is just in the States anyway, just a lot of Salmonella in these steps still. Here's a PAA spray cabinet, 200 to 300 ppm peracetic acid. After they've been transferred from the kill line to the evisceration line, again, prior to opening the carcass. This is a different plant, by the way. Here's the spray cabinet just after the evisceration steps. And you can see the mist of the spray here. So we had a spray cabinet before evisceration, spray cabinet after evisceration, and here's the same cabinet showing the spray. See the chemical coming out here of going off the birds into the, and also some into the cavity. The differences in cabinets are things that we can discuss later. The next step for most plants, and again, there's each plant is different. There's where they remove the necks, they get some neck skin off, so, other steps there. But in general, every plant has these one or more of these IOBWs, these inside-outside bird washers. Large volumes of water to wash the carcass inside as well as out. And it's mainly to rinse things off, get rid of digesta, things like that, make them look nice and clean for the inspectors. But there's an option here to add also chemical intervention, in this case, peracetic acid. Now, in this case, we have birds moving through an IOBW cabinet, pre and post IOBW. Afterwards, this plant has a post IOBW dip or pre-chill dip. The dip has, immersion dip has about 600 ppm peracetic acid in it. In this case, the IOBWs have about 195 ppm in the spray. So the birds move through the IOBW and then to an immersion dip tank, and they get very nice kill levels through this system, where they get, 4 logs, 10,000 or more counts, down a log and then down another log almost through their post-chill dip. So these are the birds that enter their chill system. So that they've done a wonderful job in reducing the load on the birds before they get into the large chill system. In this case, fresh PAA is added to the dip tank during processing. There's an overflow, always an overflow for an immersion dip tank. And the overflow for this dip tank is used to supply chemical to the IOBW. There's more supplemented into it, but it's a nice way to save some money. And the other option, of course, is to send it to the drain. It wastes both water and dollars in general. And there's an importance to the industry for water savings in general, just to reduce water costs and also to decrease the total volume of wastewater. It helps in both of these aspects. Here's antimicrobial applications on a brush cabinet and also in a dip tank. A little movie here. It turns out, although it's counterintuitive, both of these applications, in this plant, we actually had a dip tank, and they replaced it with these brush cabinets. They use the same amount of chemical per day in each application. It's just the initial fill of the chemical into the dip tank is the only difference, and it's minuscule compared to the whole day of processing. But we've got PA and brush cabinets and then an immersion dip tank. And just to show you, birds move along in there. There's no birds on the shackles in this case. I didn't have an opportunity to get to the birds moving through the dip tank before they took it out of this particular plant to change to an immersion cabinet, the brush cabinet. But in that particular brush cabinets you saw and this plant, I had the opportunity, I have many years of data of efficacy of the dip tank. Oh. The dip tank, and we got a log or more reduction for APC or EPC using the dip tank. With the brush cabinets, they're new brush cabinets, brand new brush cabinets, I might add. They haven't yet to sit there for long periods of time. We're getting less than half the results in terms of efficacy of dropping the load on birds that enter the chiller, because this is the final step before the birds enter the chiller. I myself worry about brush cabinets. They're never maintained as well. The brushes aren't replaced as often as they should be. They get frayed, and they act as little depots, in my mind, in my opinion, for pathogens. And so they sometimes spread more pathogens than they do help reduce them. Here's the chill system. So birds that enter the chill system here, there's a little bit of, this is a little bit higher, the pre-chiller here. This is the pre-chiller. We're going to have an unloader at this end. We're going to have a rocking bar that moves the birds back and forth. And birds that fall into the pre-chiller here just push mass migration here of the birds as they move through the chiller. See the unloader removing the birds, and the birds are just getting beaten there. The beater helps to increase the cooling efficiency. There's peracetic acid in the dip tank, in this chill tank, so it helps spread the antimicrobial around, and so it keeps things moving. After this, the birds move into a middle chiller and then a final chiller. And here we have an auger, large augers in both of them, both of those chillers that move the birds along in the chill system. The agitation in this case is performed by bubblers, just using air that comes up from the bottom and again, increases the cooling efficiency, and it aids in the distribution of the peracetic acid or any antimicrobial you're using. For this plant, the birds exit their final chiller, fall down into a hopper, and then are taken by a conveyor belt up to the next step. Here we have a picture from atop there where they're moving up. Just as a note, at the top here, we're going to find out there's another final post-chill dip tank that has peracetic acid in it. In this case, this processor, excuse me, all birds that are out of flow, or they're from yesterday or something like that, all go back into this. They get a peracetic acid treatment before they go into the rest of second processing. Now, this processor's found that to be very beneficial. Now we're going to see at the top of the tank, I've got a little bit longer video here showing what the dip tank is up there. This is just, they manufactured it, I'll say in-house in the plant. The birds are coming out of the chiller. And I'll just start this, turn off the noise here. So birds are moving down to the dip tank. Moved about, those bars do help them keep them submerged some. Here you'll see this cascade that puts chemical into the tank. We'll see it again. So that is fresh peracetic acid into the tank. Here the birds are moving out, and we have spray, again, fresh peracetic acid, sort of like a shower as they leave the bath. And this flows back into the tank as well, so that's not just wasted chemical. Again, that cascade, adding the fresh chemical. Here's a view in the tank as a capacity. There's not many birds going through at a particular time here. It's I'll say it's when they're the most I've ever seen going through the dip tank. Still, the birds get submerged. The antimicrobial is added, the peracetic acid, the fresh peracetic acid is checked during these times. It doesn't lose any of its target ppm level. We keep it at the correct amounts, so the processor always is assured that all the birds inside and out, all the carcasses are getting treated with what they needed to be treated with. Here they are, showing them coming out, and then for the next step, you see, and then note here too, some chemical inside the carcasses are coming down to the birds, with the birds along the trough. And this is cold rehang. This is where the birds are rehung for second processing, where they're going to be cut up and the like. But this racetrack here that they call it, the birds move around in a circle. The gloves of the workers eventually get coated with peracetic acid from this peracetic acid that flows down and is on these surfaces. It turns out very handy, I believe, in terms of keeping cross-contamination down. Now for this particular plant, we have birds coming in from evisceration at these levels of APC and EBC. After the pre-chillers, they're knocked down to these levels. After their main chiller, both main chillers, and then after that dip tank that I showed you with the peracetic acid. So very low levels coming out and flopping, I'll say flopping onto the cold rehang table for that to be rehung and then go on to second processing. So that wasn't, people do make those dip tanks, but they're mainly manufactured in-house. This is a company called Morris that sells these, I'll say, compact dip applications. COPE just stands for their trade name for Continuous Online Pathogen Eliminator. And you can see they look like little mini chillers. So really it is in there, in there is just a big unloader, very small volume. And birds fall in there, they move around, they get flopped out, and that is the dip tank. You can't see into it and you know, they do perform well in most cases. Again, it's how people run it. But part of being able to run it is being able to look at it. If that dip tank that I showed you in the previous videos didn't have enough chemical in it or everything like that, you'd notice, you could see it. This, I don't know what's going on inside of there. That is just one drawback. But if it's well managed, I do believe it can be effective. Various sizes they make for small applications and that. Again, if you're stuck for space, these may be options. And so we have many of our plants that we're in use these types of dip applications. Here's an example of a plant I'm going to talk about that actually used the COPE to good means. This is a plant X. This is a case we did. This is a plant in the western part of the United States, where if you look at the levels of birds at hot rehang, again, this is where the birds are taken off of the kill line and transferred to the evisceration line. The carcasses are warm. Here we call it the hot rehang table. And we have these levels of APC and EBC on the birds. In the plant, they have a small, very small peracetic acid spray cabinet. It's there for regulatory purposes only, for something we have called an online waiver. But you'll see that the plant does not get much of a kill all through their evisceration. In here is evisceration, the IOBWs, anything else, neck skin cutters, all of that is in this section. At the end, they've got this small booth that is not adequate, doesn't even spray to the inside cavities of the birds. They also have salvage birds, and salvage birds are birds taken off the line here, taken off to a different area. They're managed by hand. They're cleaned, they're vacuumed, cleaned, diseased parts are cut off and the like. And they eventually get back into the chillers. And that's the problem. All these birds get into the chillers. And the reason they came to us, the reason I was doing all of this is because this plant was having problems with salmonella post-chill. And so we went in there to find out, well, what's going on? And so what we like to do is to perform biomapping to see if we can see if there's any obvious problems. Well, this is one we noticed, and the salmonella levels on these, I didn't show these data, but are high on this for this plant. And just as a note here, the plants use chlorine, hypochlorite, 50 ppm in salvage, where the birds again are cut and cleaned, and they're sprayed with a hose by hand, also in and out, sometimes sunk in a sink of 50 ppm hypochlorite. They still have these levels. The plant uses hypochlorite, ppm on all their machines, bird washers, hypochlorite, all through these processes, and they're still at these levels of bacteria on the carcasses. So again, the problem was that, now here's an overview. This plant we just showed the evisceration portion. Now the birds going into the pre-chiller and the birds coming out post-chill still had large amounts. For industry standards, these numbers are large for coming out of a chiller. So this plant had the evisceration, goes into a pre-chiller, a main chiller, and a final chiller. Still, they're getting these large numbers coming out. Now, what the plant did here is they added one of those copes, one of those large copes that had the diameter of their chill system. So you can imagine this cope unit, this dip tank, this vertical dip tank, if you will, right before their chiller. So the birds from evisceration, instead of going right into the chiller, pre-chiller, go into this cope unit. And you can see that this cope unit serves to reduce before and after the cope, easy to get the birds to do these microbiological measurements, get a nice reduction here. So before they enter their chill system now, they've got lower levels. And it turns out that they did very well post their final chiller, getting very low numbers again. And again, the previous results had, without that cope unit in here, this bar was here at 2.7. This went from 0 to 0.58 logs of Enterobacteriaceae. But more important for the plant was this. Before they had the, coming into the cope from evisceration, they had 100% incidence of Salmonella and Campylobacter. And right away after the cope, knocked down a number 2, more reasonable. And I say that's much more reasonable, much more, I say that's better than 50% is because the number of organisms per carcass here is not known. This could be many, many, many hundreds even of Salmonella organisms per carcass. So remember, this 50% levels mean, every other bird has one Salmonella on it, right? Or maybe a couple. So it really reduced, I believe, well here for both Salmonella and Campylobacter, and the rest of their chiller seems to take care of it. And their actual numbers that they worry about because of the USDA inspectors, when they take the carcass rinses, they get 0 results, which is what the plant wants. So now I'm going to go into second processing. For years, this was all the interventions that plants had were in first processing. And again, the post-chill number, because that's where the USDA inspectors did their sampling. And that's how they evaluated your plant, how well you were performing right there. Well, it turns out USDA started looking at second processing. Well, why was this? Well, plants were performing very well, it turns out. Meeting the USDA targets that we said we need to reduce Salmonella to. They did it. But salmonellosis, human sickness with Salmonella, wasn't decreasing as much as they thought. So we might think that it's maybe they ought to look at lettuce or raspberries or something. No, they decided to look at chickens in second processing. Well, it was found that bacterial counts, as well as the incidence of pathogens, do increase as carcasses are processed, handled, cut after chilling. And the industry responded by adding applications in these areas. Now, these applications you're going to see do reduce pathogen incident, but they also do something that's beneficial in terms of reducing spoilage-causing organisms, and therefore helps to improve product shelf life. And for customers that need fresh product and things like that, extended shelf life, or packaged products in a grocery store, a very important to their to reduce the any returned product. So their bottom line was positively impacted in that regard. So here's the example I'm going to show. This happens to be that same plant, by the way, where I was just showing what that had to dip into the cold rehang table. You see the cold rehang table we were assessing here. We're looking at microbiological levels on breast pieces, whole breasts. And at cold rehang, now this is a whole carcass rinse here, right? This is the level of bacteria. Now you take some of these carcasses, these breasts, put them in a rinse bag, you shake them with the sterile rinse buffer, you get much higher levels of both indicator organisms on that. So they add a dip tank. Start it again. And you can see this dip tank, 1, 2, 3, 4, 5, 6, so maybe 7 or 8 seconds of dip tank. It's around 700-800 ppm peracetic acid, and they exit. And using that dip tank, they get a nice reduction in counts of the indicator organisms. This same plant has 2 lines for breasts. These are the skinless whole breasts. This dip tank you can see is shorter. I don't have a video for this. Again, we're starting at cold rehang, this level of the indicator organisms. After you take the skin off, right before it falls into that dip tank, it's increased. They get less reduction with less length of the dip tank, I believe, less time, less dwell time in the presence of the chemical, and it might be expected, but still, and then right now they're looking at moving this dip tank to a place from here. Further on the other side of this, there's a wall back here where they can get a larger dip tank in to mimic the size of the tank they had on the line on the left. Here's a different plant that uses breasts for all sorts of things, but one of the things it does do with breasts, it goes into grind. They make a white chicken ground product with it, very valued product for them. And one of the problems with all ground products is the level of salmonella, as many of you know. So what these folks do, they take the breasts, and these are post-skin breasts in this case, and they moved along transport belts to a dip tank. And you see, just moving along this transport belt, they've gained in bacterial counts. They put them through a dip tank, they knock everything down again. And then again, what happens here? The breasts are transported, they collect them into 2,000-pound combos, big storage tubs, then store them for 12 hours, in a cold room, used to feed the grinder. And these breasts here were sampled as the combo was rolled in to be ground. So nothing's been done to them. They haven't been ground. They've just spent time in the combo, and the counts went from here to here. And so this is just, you can see, a tool to look at where problems may be in your process that you can maybe address to optimize your use of antimicrobials, or maybe somehow change your process to where this dwell time, this time spent here is shorter, or add interventions in this step before the grinder, which they eventually went to. Here's a video. I'll show you. This is boneless, skinless breasts, and the worker there is arranging the breasts so they're kind of spread apart. And they don't do that unless I'm there taking pictures. but you can see that's a very short and shallow dip. Not much happens to them in terms of agitation. There's not a bubbler on that, and it falls off onto this white belt. And I add that as, and I say that. We didn't have a chance to work with many of these plants. The USDA, when they decided they're going to do testing and second processing, all the plants went on their own and put in all of these applications. We are trying to help plants either modify their existing processes or instruct them on how to put new things in I'll say properly, or to maximize their efficacy, to make better use of their dollars spent on peracetic acid and what we do with them. Oh, no, go back up again. Here's that white belt. They go up the white belt, and they'll eventually make it to a hopper where they're bagged directly. Up here, there's 2 spray nozzles, usually just to spray a little peracetic acid on it. It keeps the belt clean more than anything else, I believe. Sprays on belts aren't really used to treat product. You can only get the top half of it anyway. And if one piece is on top of another, you can't get any chemical to those surfaces that are hidden. And for this plant, we have boneless, skinless thighs pre-dip, and then post-dip, we get an okay, I guess, reduction. It could be a lot better, I believe, if they modify their dip tank. And then at the hopper, where they're bagging the plants, they get an okay, a fairly stable level of these indicator organisms across. Their problem is they have all of these, they have very high levels of bacterial load coming in. It turns out that these are at least day-old boneless, skinless thighs. And so that's something they're working on to reduce the pathogen load at that step before they enter the this stage of the process, before they get close to bagging in the final product. And this is where USDA does their assessment. Okay, this happens to be a plant that processes tenders. They have a deboning machine that produces the tenders. They go along a long belt where they have an X-ray and then onto a dip, 700 ppm peracetic acid dip. And then they take the tenders and they slice them in half lengthwise. So at the start of the process, coming out of the deboning machine, we have this level. They move on a belt here to the X-ray and before the dip, and we selected right before the dip. Now the X-ray machine is prior to this, but all the time while this X-ray machine is running and it catches something, it dumps the product, the tenders with the suspect piece in it, right, back, and they recycle back over. And so we've got this recycle step. We've got this buildup, I believe, of contamination, cross-contamination during the day at this step, because we've got this kickback of product that's sort of recycled. So in the dip, they get a nice kill, but then they go on a series of belts to a slicer. And at this stage, for the tender slicer to work properly, they have right here many workers handling, lining the tenders up to be sliced. So there's a lot of handling here. And then after the slicer, we have this large increase again, and also increase in salmonella. And that's their main concern, because that's right where these are bagged and where the inspector takes the check. So we're talking about moving this dip from this spot to an area after the slicer, which may solve a lot of their problems. We've got new exposed surfaces with the sliced tender and the like. Here's an image of a bone-in, skin-on thigh dip. I wanted to show that to you because it's a really thin dip. It's a little deeper maybe than some, but we can use this to our advantage sometimes based on your logistics. Every plant is different in a way to treat product effectively. Here they are exiting. You'll note here in this plant, this is supposed to be adding fresh peracetic acid, and someone's forgotten to turn it on. the reason I took this photo was to tell management that, you know, we need to have somebody looking at this to make sure things are running correctly. Here's just I'm going to get close to the end here. Just a couple of videos of, in this case, we've got leg quarters moving through a dip tank. Not as in focus as I like, but this does have bubbling agitation in it. Notice too, in most of these cases, we don't have much foaming in the dip tanks, which sometimes can occur. Here we have whole wings. Here we have whole wings going through a dip tank. Much the same story. We have an interesting case here of a process that uses mechanical deboning of leg quarters. For this particular plant, they have leg quarters falling onto a belt. As they fall onto the belt, the leg quarters, we took samples of them, and we get, you know, maybe 2 logs, half a log of aerobic and enterobacteriaceae counts on them. They go through this very long belt. It literally is, it's at least 100 yards. It's way up in the sky. In the sky, I'm meaning it can be missed by sanitation crews easily. And sure enough, when they fall off that belt into the area where the deboning machines are, we have this rather large increase, 2 logs almost, of these indicator organisms. And you can bet if the indicator organisms are increasing, Salmonella is also increasing. Then they go through their deboning machine, another increase. Then they go through manual trimming. And here we had our largest increase. I mean, those are, you know, that's 100,000 bacteria here, 10,000. And I just want to say we did also salmonella mapping through here. All the samples we had here on some days, all the samples here were 100% salmonella positive. They put them through a cope, small cope unit, and they get this nice decrease. They have tolerable levels of salmonella in their mind, but still, these data allowed them to sort of look at, what are we doing here? Are the workers sanitizing their gloves off break? Are we rinsing our tools? Is sanitation crew doing their job here? These are all things we like to look at. I like to look at to help save problems, because in the end, it's our peracetic acid that has to do the job. We want to make it easier for the peracetic acid to do the job. Here's just a picture of a peracetic acid wing dip. And with that, I'll see if there are any questions.
Thank you, John, for your time, and the presentation was very good. No sé si tienen alguna pregunta, alguna duda, para que nos la manden por el chat para hacérsela al Dr. Dankert. John, before everybody starts to ask, I would like to ask you, what do you think is better, to immerse the bird on the deep tank or spray it?
Immersion.
Okay. Yo le hice
Immersion
la pregunta.
I have so much data that shows that any immersion tank can beat any spray application, and you have to keep in mind that it uses the same amount of chemical. So.
Okay. Le hacía la pregunta yo al doctor que qué era mejor, si inmersar o poner en inmersión el pollo, la carne, lo que vayamos a hacer, o esprearla. Y él, la respuesta que nos daba era que en la experiencia y la data que él tiene es que es mejor hacer una inmersión de lo que vayamos a desinfectar en el lugar, y que al final consumen la misma cantidad. Podría parecer que la aspersión consume menos, pero él decía que consume lo mismo. The other question, John, in Central America, maybe recently, we start to measure Campylobacter on the birds. Usually we just measure Salmonella. In Campylobacter, how it reacts, how it performs peracetic acid compared to chlorine? In your experience, what you have seen? Just allow me to translate the question before you answer. Mi pregunta era que en Centroamérica últimamente se empezó a medir el Campylobacter, que antes solo era Salmonella. ¿Cómo es la experiencia de él en cuanto a la eficacia del ácido peracético comparado con el cloro en Campylobacter? John, so you can answer it.
Yes, Campylobacter in the States is still not a regulatory, the USDA doesn't test for it yet officially, but unofficially they do, and they are going to start officially doing it. So plants are for the past few years have been working diligently, and so have we, on Campylobacter. All I can say is that for all this, everything that's been tried, and we try a lot of different chemicals, peracetic acid is by far and away the best for Campylobacter, as well as Salmonella. I don't see there's any competition. Lots of these plants use, well, I'll confess that the only places plants use hypochlorite a lot of is maybe on evisceration equipment to keep the equipment clean. I'm not sure that it actually works. It does anything. I always like to make sure that any antimicrobial I'm adding is actually better than water, and I just haven't found that for controlling Campylobacter. In our experience, Campylobacter is controlled for the most part. The lion's share of it is taken down in the chill system, and specifically the pre-chiller. The pre-chiller knocks things down, Campylobacter down very well. I did have a slide there that did show that for that one plant. And so proper treatment of the pre-chiller, and again, with peracetic acid, seems to work well in knocking that pathogen down.
Ok, thank you. La respuesta que me dio a la pregunta es que es muy superior el ácido peracético en aplicaciones tanto así como en resumen de pre-chiller, chiller y post-chiller en cuanto a manejo del Campylobacter, que son muy superiores los resultados, que realmente la mayoría de lo que ha visto es el uso de peracético. I have another question, Mr. Dankert. Is from Samuel Garcia. Hello, I got a question. Comparing another disinfectant and sanitizer, how safe is using peracetic acid directly comparing alcohol, chlorine, and many others? Thank you.
Well, alcohol, well, that I've not heard of used it for meat processing, but you know, it dries the skin out and things like that. And peracetic acid is acidic as lemon juice would be. And it is just, I'll have to say, for the concentrations you use where you get a smell, peracetic acid is much more effective than either. Well, I think for hard surface disinfecting too, comparing alcohol to peracetic acid is much better in terms of efficacy against. And now, again, those are medical pathogens and the like. But in terms of chlorine, comparison to chlorine, hypochlorite in this case, there's not a comparison in terms of efficacy. In terms of smell, you'd have to get a large, high concentrations of peracetic acid in the body of water or the spray. Well, I guess unless it's sprayed directly on you, I guess you have a nozzle that's spraying on you. That would be, you know, I guess in your eye or something. But chlorine also has the ability, in this case, to react with amines and make di and trichloroamines. I mean, even at low levels. And these can serve as eye irritants and nasal and back to your throat kind of pains. The trichloroamines and that's been known for years when chlorine is used at high levels. And of course, there's a lot of amine groups when there's protein involved. So in general, I think chlorine has more of I'll say a smell issue, put that in quotes, versus peracetic acid. Anyway, that's our experience.
Okay, thank you, John. Another question. I don't see any more questions, but I have a question. In the US, John, if you can answer that, what is the most poultry plants, what are they using? They're using chlorine to disinfect carcass, or they're using peracetic or cetylpyridinum? What are they using in disinfection of poultry in most of the plants in the US?
Oh, I don't know of a plant that uses chlorine for disinfecting, like in the chiller anymore. No one. If they want to meet a USDA standard, unless it's maybe plants that I'm not aware of, like very small plants, a couple hundred birds a day or something, or backyard facilities. But for large processors, I'm sure it's got to be 98% of the processing, the actual pounds produced in terms of that. Don't use chlorine. If it would work, if it could have been made to work. Now, years ago, you go back 15, 20 years, yes, they used chlorine, but the standards were not as high. To meet the standards now, they cannot use chlorine. They would use chlorine if they could, but they all use, as far as I know, peracetic acid for all of these applications. Certainly, when the USDA came out with the second processing standards, I don't know anybody that stayed with chlorine. I mean, they were generally in second processing using chlorine on their machines and things like that, and the water had a few ppm of chlorine in it, but it was nowhere near enough to meet the standards that the USDA required, and so everybody switched to all the new applications were peracetic acid. Yeah.
Okay, perfect. Thank you. There is another question, I think, that is most on surface disinfection is, hello, does PAA reduce ATP level as facility sanitation?
ATP level?
Yeah, imagine it's for surface.
Yeah, well, in the States, by law, this is a food processing aid that can't be used as a hard surface disinfectant. But we have a product, Blitz, I believe it's called Blitz. We have a peracetic acid that works very well. I mean, it's the same chemical, but it's got a different label on it. It's got an EPA label as a hard surface disinfectant. It works very well as a sanitizer and disinfectant.
Ok, tal vez solo para aclararles, ellos manejan diferentes formulaciones. La que él habló aquí, el peracético, que era el Spectrum, solo se usa por ley en Estados Unidos para desinfectar el pollo. Para desinfección de superficie se usa Blitz o Vigorox. A la pregunta que hacía el señor Roberto, el ATP normalmente le va a interferir el peracético por tener producto orgánico, por ser una materia orgánica, le va a subir y le va a alterar la medición de ATP. Normalmente por eso el ATP, inclusive el amonio cuaternario lo interfiere. Por eso el ATP se sugiere pasarlo después del detergente. Hago el detergente, enjuago y de ahí paso el ATP. Productos como el peracético sí le va a alterar, le va a subir, le va a tender a subir porque tiene componente orgánico y eso es lo que está midiendo el ATP. Based on your experience, John.
Oh, if I could just one point here before that brought up a thought in my mind. When remember I talked about the belts that are high in the air, hard to sanitize. They're very long, maybe not cleaned properly. The addition of a peracetic acid spray, it hits a part every once in a while that goes under it. But I believe it's more important that we spray the belt, got the surface of the belt, so that all the old built up material there, I believe that is cross-contamination, can be limited. during processing. So in reality, we use Evonik on sprays. I like it on belts because for that reason, just to keep the belts clean, not the chicken per se.
Ok, pues gracias por el tiempo que ya nos pasamos. Thank you very much, Mr. Dankert. It's a pleasure to have you as a presenter. Thanks for everybody that is here. A todos ustedes les agradecemos mucho su tiempo y feliz tarde. David, no sé si está algo más. Creo que gracias a todos nuevamente.
Sí, estamos súper bien. Gracias por la participación y los esperamos en la siguiente conferencia.